Okay, so this is the first part of the multiple choice review. This is all about limits and continuity. The big idea to kind of navigate through these 15 problems is you need to understand what the definition of a limit existing is compared to the definition of continuity. And that's kind of a sticking point that they like to try to nail you on the AP exam. So really quick, for a function to be continuous, or for the limit to exist rather, it doesn't matter that I have a hole hanging out right here. So remember, the idea for a limit to exist is we look at the function approach from the left compared to how it approaches from the right. As long as it's approaching the same value from each side, that limit exists. So both the left and the right hand have to be approaching the same number from both sides. In this case, I'm going to say this is A, this is the limit as x approaches A of the function. This exists because as I come in from the left and as I come in from the right, I'm approaching that same value. Limit exists. Now, for the function to be continuous, there are three things that have to happen. The limit as we come in from the left and the right has to exist. Okay, so this would hit that first part. F of A has to exist. Now for us, F of A does not exist. There's a hole there. Okay, so if I came in and this nice little blue dot, decided I was going to patch that hole exactly right there, well, now F of A exists. And F of A equals that function's limit as it's coming in from both sides. So this is a continuous function. F of A exists and F of A matches what the limit is. If I move this guy up here, F of A exists. We've patched that hole, but the function is not continuous. That's a nice little 2-minute review of what makes a function continuous versus what makes it have a limit that exists. First part that we're going to talk about, and this is a tough one. I'm not going to lie, this is one that we definitely haven't seen since chapter 2. The idea is you have this piecewise function that you're kind of creating. This guy is not going to be defined at 2 because of the denominator. What you want to do is you want to patch that hole at 2. So you need to find that k value that's going to allow you to patch that hole appropriately. So this is the function. You rationalize the numerator, which is something that we haven't really seen since chapter 2. So you'll see that it matches, except it says plus. When you multiply that out, you get 2x plus 5 minus the quantity x plus 7. Be careful with how you write that. In the sense of this guy has a negative, which is why we had a negative with that entire quantity, because it came from squaring of a radical. The denominator I just left as a mess, and I would just leave it as a mess, because the numerator simplifies down into x minus 2. These guys go away, so now I'm left with 1 over all of that. Replace your x with 2. You get 1 over radical 9 plus radical 9, 1 over 3 plus 3, 1/6. Number 2, the answer was C. If f is a continuous function on A and B, what is necessarily true? Well, if it's continuous, this is kind of a different play on the idea of your definition of continuity. It's just nicely, it's worded very differently. So as x approaches that x sub 0 value of that function, it's going to be the same as what that function is defined at. 3 is a nice infinite limit, or the idea of end behavior asymptotes. So in this case, you have the same power in the top as you do in the bottom, the same degree in the top and the bottom, I should say. So you're looking at the ratio of the coefficients, so the limit's going to approach 4. There were 3 different cases for end behavior asymptotes. If you have the same, then it's the coefficient, which is what we just saw, the ratio of the coefficients. If I had something like y, we'll call it x cubed over x squared, this would be a slant asymptote, and your end behavior would be at y equals x. You have to do the division. If I had this guy, it would be at y equals 0 because you have the bigger degree in the denominator. Number 4 is one that we had to memorize in chapter 2. This is the limit as x approaches 0, so it's kind of your first ding that we're focusing on the origin. Rewrite cosecant as 1 over sine. Hopefully that looks familiar. It's equal to 1. This next part, so this is where they're trying to get you on the definition of continuity versus the definition of a limit. So what this is saying is you have a limit that exists at A. This is my A hanging out here. You just know at A the limit exists. And what it is at A is equal to L. Could be an open dot, could be a closed dot. We really don't know. F of A, or the derivative of A exists. Well, if it's an open dot, the derivative does not exist. And because with the definition of a limit existing, and the fact that you don't have to actually the function does not have to be defined at A, that does kind of throw a monkey wrench in the gears about having a derivative exist. Same with if there's an open hole here, you can't assume that that function is continuous. You can't assume that that function is defined at A. That's not part of the definition of a limit. You also can't assume that the function being defined at A is going to be L. So part D is saying, well, f of A is equal to the limit. Well, that has nothing to do with the definition of a limit existing. C is saying that you do have an actual value at A. You don't know that. B is saying that it's continuous, which basically is going to go along with C and D. But you don't know that that function is continuous. And if there is a hole here, then that function, it does not have a derivative. So this would be none of the above. 6 plays on the same exact premise that we just saw. So this is saying I have some function that as I approach 3, the limit is 7. So I'll have this guy come down. But once again, you don't know if that's open or closed. So is f continuous at 3? Well, for it to be continuous at 3, we'd have to have this guy patched, and we don't know necessarily that it's going to be patched. Is it differentiable? Well, if it's open, you can't have a derivative there. F of 3 is equal to 7. You don't know that. All I know is the limit exists. I very well could have it patched there. So this is going to be A, none. Number 7, this is a limit as h approaches 0, so be careful with this. When h approaches, we have h approaching 0. That's your change in x is approaching 0 on your tangent line. So remember we were talking about this is A plus h. The closer that we're getting, we're looking at, we want the h to basically be non-existent. So you want that change in your x values to be non-existent as well. So we're really asking if y is equal to sine of x. So this is your x plus h in your, hopefully that kind of rings the bell. Your function is sine of x. It's really saying, what is the derivative of sine of x? Well, the derivative of sine of x is cosine of x. Be careful. Don't let this idea that h is approaching 0 make you think, oh, well, that's when x is equal to 0. We're not saying that. If I wanted it to be at 0, we would say as x approaches 0. So just be careful with that and make sure, because I think when you look at this, you could have thought, oh, well, that's going to be cosine of 0 would be equal to 1. That's going to be 1. Well, you kind of took it a step too far. This is really just asking what is the derivative. This is another infinite limit situation. So what you're looking for, same degree in the top and the bottom. So it's going to be the ratio of the coefficients. Number 9 is a nice one. This is a little bit of Pythagorean relations that you have to remember. So what I did is I factored out the 2, took out sine and replaced it with 1 minus cosine squared. So sine squared of theta plus cosine squared of theta is equal to 1. Solve for sine, and that guy went in. Factor the bottom into the difference of squares. This cancels. So now I have 1 in the top, 2, and that's 1 plus cosine of theta. Place your theta with 0. Cosine of 0, hanging out right there. That's your base is 1. Simplifies down into 1/4. This guy, not a bad question. You're probably going to see it in some way, shape, or form. So this is basically a play on kind of the idea of the derivative, not exactly. So f of x, I replaced and put that guy straight in, right here. Then I put f of 0 in, simplified, and you had 2x squared in the top. I messed up in my very first step and went ahead and did that x as 0. Went back and just made it into x squared because I saw that once I did that, if I made it into 0, I had 0 in the denominator, and that was really like, ooh, I didn't like that. Made it back into x squared, so I had 2x squared over x squared. Those guys cancel. The answer is 2. Number 11, so this is another one where it's the definition of continuity versus limits. You saw this one in chapter 2 on your test, and you also saw it in some warm-ups, but it is that guy right there. Limit as x approaches a is the same as limit as x approaches b. The limit at a is 2. The limit at b, because they're not approaching the same value from the left and the right. From the left he's approaching 2, from the right he's approaching 1. There is no limit at b. The limit at a is equal to 2. What that says? Yeah, we'll go with it. Let me erase this really quick. Okay, so this guy does not exist. I may have circled the wrong one. I can't really read him. So it does not exist. So as x approaches a, the limit is equal to 2. Well, we kind of just determined that, so that one has to be true. The limit at b equals 2. We just decided there is no limit at b. The limit at b equals 1. Well, that's false. The limit does not exist. The limit at a does not exist. That is false. The limit at a is 2. So sorry, it should have been b is the correct answer on that one. This one is just good old-fashioned plug and chug, so throw 1 in for each of those. There's nothing you can do with natural log in the denominator. There's not a way to fix it or rationalize it, so it's a direct substitution. And when you do that, you get 1 over 0, therefore that limit is non-existent. And 13, we have this function. This is your difference quotient, so this is some function at 2. So some function at 2. And it has a derivative. So this function at 2 has a tangent line, and the slope of the tangent line is equal to 5. That's basically what we know. Is it continuous at 2? It has to be. For it to have a derivative, it has to be a continuous function. Is it differentiable at 2? Well, that's the definition of a derivative. You told me it equals 5, so yeah, it is differentiable. Is the derivative of f is continuous at 2. The definition of the difference quotient and of a derivative doesn't talk about the derivative being continuous. So with the information that we have, we can't make an assumption about 3. So C, only 1 and 2. And this guy, the graph of f is shown above. Which one of the following statements is false? It's continuous at x equals a. Well, when you look at x equals a, right there, does it match the definition of continuity? Nope. So it should be a. I think that's all I have to say.